Welcome to Cosmic Serenity, where we explore the fascinating intersections of space, science, philosophy, and the nature of existence. I'm your host, and today we're delving into a topic that seems to bridge the gap between science fiction and reality: directed energy weapons, or DEWs. These advanced technological marvels represent a significant leap forward in the realm of weaponry, utilizing highly focused energy to achieve their objectives. So sit back, relax, and join me on this journey into the world of DEWs, where we'll examine their types, advantages, challenges, current status, and the ethical considerations surrounding their development and use. As we begin our exploration, let's take a moment to center ourselves and contemplate the broader implications of such technology. The development of DEWs raises profound questions about the nature of conflict, the ethics of warfare, and humanity's relationship with increasingly advanced forms of technology. These are weighty matters that touch upon fundamental aspects of our existence and our place in the cosmos. Now, let's start by defining what exactly we mean by directed energy weapons. At their core, DEWs are systems that emit highly focused energy, including electromagnetic radiation, particles, or sound, for the purpose of damaging or destroying equipment and facilities, and in some cases, incapacitating personnel. Unlike conventional kinetic weapons that rely on projectiles, DEWs harness the power of energy itself, manipulating it in ways that can seem almost magical to the untrained eye. The concept of using energy as a weapon isn't entirely new. Throughout history, humans have sought ways to harness and direct energy for various purposes, including warfare. From the use of fire in ancient times to the development of gunpowder and explosives, we've long understood the destructive potential of concentrated energy. However, DEWs represent a quantum leap forward in this lineage, offering capabilities that would have been unimaginable even a few decades ago. Let's delve into the main types of directed energy weapons, each with its own unique characteristics and potential applications. First, we have high-energy lasers, or HELs. These weapons utilize intense beams of coherent light to deliver destructive energy to a target. The concept of laser weapons has long captured the public imagination, featuring prominently in science fiction stories and films. But the reality of HELs is no less impressive than their fictional counterparts. At their core, HELs work by concentrating enormous amounts of light energy onto a small area. This causes rapid heating of the target, leading to structural damage, component failure, or even complete destruction. The power of these lasers is truly staggering, with some systems capable of outputting hundreds of kilowatts or even megawatts of power. One of the key advantages of HELs is their precision. Because a laser beam travels in a straight line and can be focused with incredible accuracy, these weapons can engage targets with pinpoint precision, potentially reducing collateral damage compared to traditional explosives. This precision also allows for engagement of small, fast-moving targets that might be difficult or impossible to hit with conventional weapons. HELs come in various forms, from relatively small, vehicle-mounted systems to larger, fixed installations. Some are designed for short-range defense against drones or missiles, while others have the potential for long-range engagement of aircraft or even satellites. The U.S. Navy, for example, has been testing ship-mounted laser systems for defense against small boats and drones. The development of HELs hasn't been without its challenges, however. Early systems were bulky, power-hungry, and struggled with issues like atmospheric scattering and thermal blooming, where the heat of the laser itself can distort the beam. Modern HELs have made significant strides in overcoming these issues, but they remain active areas of research and development. As we contemplate the existence of such powerful laser systems, we might pause to reflect on the dual nature of technological progress. The same principles that allow us to create these weapons also drive advancements in fields like communications, manufacturing, and medicine. It's a reminder of the responsibility that comes with knowledge and the importance of guiding our technological development with wisdom and foresight. Moving on to our second category of DWs, we have high-power microwaves, or HPMs. While HELs rely on intense visible or infrared light, HPMs harness the power of microwave radiation. This type of directed energy weapon operates on principles similar to those used in your household microwave oven, but at much higher power levels and with more precise targeting. HPMs work by generating powerful bursts of microwave energy and directing them at a target. When this energy encounters electronic systems, it can induce powerful electrical currents, overwhelming and potentially damaging sensitive components. In essence, HPMs are designed to disrupt or destroy electronic equipment rather than cause physical destruction through heat like HELs. The potential applications of HPM weapons are particularly relevant in our increasingly electronic-dependent world. They could be used to disable vehicles, knock out communication systems, or even render entire facilities inoperable by damaging their electrical infrastructure. Some HPM systems are designed to be non-lethal to humans while still effectively neutralizing electronic threats. One of the most intriguing aspects of HPM weapons is their potential for use against hardened targets. While physical armor can protect against kinetic weapons and even some laser systems, it's much more challenging to shield against high-power microwave radiation. This makes HPMs a potentially valuable tool for dealing with targets that might be resistant to other forms of attack. However, the widespread use of HPM weapons also raises concerns about the vulnerability of civilian infrastructure to such attacks. In an age where so much of our daily lives depends on electronic systems, the potential for disruption by HPM weapons is significant. This underscores the importance of developing robust defensive measures alongside offensive capabilities. As we consider the implications of HPM weapons, we might reflect on our society's deep reliance on technology. The potential vulnerability exposed by these weapons serves as a reminder of the delicate balance we strike between technological advancement and security. It prompts us to consider questions about resilience, redundancy, and the wisdom of placing so much of our civilization's functioning in systems that could be disrupted by such means. The third category of DWs we'll explore is perhaps the most exotic: particle beam weapons. These systems, which are still largely in the theoretical and early experimental stages, would work by accelerating subatomic particles to extremely high speeds and focusing them into a coherent beam. The concept behind particle beam weapons is to deliver kinetic energy at the subatomic level. By accelerating particles like protons or electrons to near-light speeds, these weapons could theoretically deliver enormous amounts of energy to a target. The impact of such a beam could cause physical damage through heating and shock, as well as potentially disrupting electronic systems in a manner similar to HPMs. One of the most significant challenges in developing particle beam weapons is the issue of propagation. Unlike lasers or microwaves, particle beams are composed of matter, which interacts strongly with the atmosphere. This interaction can cause the beam to lose coherence and disperse before reaching its target, limiting the effective range of such weapons. As a result, much of the research into particle beam weapons has focused on their potential use in space, where the lack of atmosphere would allow the beams to maintain their coherence over much greater distances. The development of particle beam weapons represents a fascinating intersection of fundamental physics and advanced technology. The same principles that allow us to probe the basic structure of matter in particle accelerators could potentially be harnessed for defensive or offensive purposes. This dual-use nature of scientific knowledge is a recurring theme in the history of technology, reminding us of the importance of ethical considerations in scientific research. As we ponder the potential of particle beam weapons, we might reflect on the human drive to push the boundaries of what's possible. From the earliest stone tools to the most advanced DWs, our species has consistently sought to extend our capabilities through technology. This impulse has led to both tremendous achievements and grave dangers. The development of particle beam weapons, with their roots in our quest to understand the fundamental nature of the universe, serves as a poignant example of this duality. Now that we've explored the main types of directed energy weapons, let's delve deeper into their advantages, which help explain why they've become such a focus of military research and development. One of the most significant advantages of DWs is their speed of light attack capability. Traditional kinetic weapons, whether they're bullets, missiles, or artillery shells, all take time to travel from the weapon to the target. This travel time can allow for evasive action or the deployment of countermeasures. DWs, on the other hand, deliver their effect at the speed of light. For laser and microwave-based systems, this means that the energy reaches the target almost instantaneously after the weapon is fired. This speed of light capability is particularly valuable in scenarios involving fast-moving targets or situations where split-second timing is critical. For example, in missile defense applications, the ability to engage an incoming threat with no travel time for the countermeasure could make the difference between a successful interception and a catastrophic impact. The speed of DWs also contributes to their precision. Because there's no need to account for factors like wind or gravity that affect the trajectory of physical projectiles, DWs can be aimed with extreme accuracy. This precision could potentially reduce collateral damage in combat situations, allowing for more targeted engagements that minimize harm to surrounding areas or non-combatants. As we contemplate this incredible speed and precision, we might reflect on how our perception of time and distance shapes our understanding of conflict. The idea of weapons that act instantaneously over potentially vast distances challenges our intuitive notions of space and time, reminding us of the profound ways in which technology can reshape our relationship with the physical world. Another significant advantage of DWs is their potentially unlimited ammunition. Traditional weapons are limited by the amount of physical ammunition they can carry or that can be supplied to them. Once a gun runs out of bullets or a missile launcher exhausts its payload, it becomes ineffective until resupplied. DWs, however, can continue to operate as long as they have a power source. This deeper magazine capability could dramatically change the dynamics of both offensive and defensive operations. A DEW system could potentially engage multiple threats in rapid succession without needing to reload, or maintain a defensive posture for extended periods without resupply. The limiting factor becomes power generation and cooling rather than ammunition stockpiles. This shift from limited physical ammunition to potentially unlimited energy-based attacks represents a fundamental change in the nature of weaponry. It prompts us to reconsider our notions of scarcity and abundance in the context of conflict. While traditional warfare often involves careful management of limited resources, DEWs introduce the possibility of abundance in firepower, limited only by energy availability. However, this advantage also raises important questions about the potential for prolonged conflicts. If weapons are no longer limited by ammunition, does this remove one of the natural constraints on warfare? How might this affect decision-making processes in military and political spheres? These are complex ethical and strategic questions that we must grapple with as DEW technology advances. A third key advantage of DEWs is their potential for reduced collateral damage. Traditional explosive weapons often affect a wide area around their intended target, potentially causing unintended harm to civilians or infrastructure. DEWs, with their precise targeting and non-explosive nature, have the potential to minimize such collateral effects. For example, a laser weapon used against a threatening drone could disable the target without creating an explosion that might harm nearby structures or individuals. Similarly, an HPM weapon could potentially disable a vehicle's electronics without causing physical harm to its occupants or surroundings. This potential for more discriminate use of force aligns with evolving norms in warfare that emphasize minimizing civilian casualties and unnecessary destruction. It also opens up possibilities for non-lethal applications of military technology, potentially providing more options for de-escalation in tense situations. As we consider this potential for reduced collateral damage, we might reflect on the ethical implications of more precise weaponry. Does the ability to strike with greater precision make the use of force more palatable? How does this capability intersect with principles of just war theory and international humanitarian law? These are profound questions that touch on fundamental issues of ethics, law, and the nature of conflict itself. Another advantage worth noting is the potential cost-effectiveness of DEWs in certain applications. While the initial development and deployment costs of DEW systems can be high, their ammunition, essentially just energy, is relatively inexpensive compared to sophisticated missiles or precision-guided munitions. For applications like point defense against incoming projectiles or drones, where multiple engagements might be necessary, this could represent a significant cost saving over time. Additionally, the speed and precision of DEWs could potentially allow for the neutralization of threats using fewer shots than might be required with traditional weapons, further enhancing their cost-effectiveness. This economic aspect of DEWs could have significant implications for military budgeting and strategy, potentially allowing for more sustainable long-term defense postures. As we ponder these economic considerations, we might reflect on the broader relationship between technology, economics, and military power. Throughout history, advances in military technology have often been driven by economic factors, and in turn have shaped economic systems. The development of DWs represents another chapter in this ongoing interplay between economic and military spheres. Lastly, DWs offer a high degree of scalability and flexibility. The power output of many DEW systems can be adjusted, allowing for a range of effects from temporary disruption to permanent destruction. This scalability could provide military commanders with more options in engaging threats, potentially allowing for a more measured and proportionate use of force. Furthermore, because DEWs operate on fundamentally different principles than traditional weapons, they open up new tactical and strategic possibilities. They could be effective against targets that are hardened against conventional weapons, or in scenarios where the use of explosive ordnance would be inappropriate or counterproductive. This flexibility and scalability of DWs prompt us to reconsider our understanding of force and its application. In a world where the effects of a weapon can be finely tuned, how does this change our approach to conflict resolution? Does the availability of more graduated options for the use of force make peaceful resolutions more or less likely? These are complex questions that intersect with issues of psychology, game theory, and international relations. While the advantages of directed energy weapons are significant, it's crucial that we also examine the challenges associated with their development and deployment. These hurdles are not just technical in nature, but also encompass logistical, strategic, and ethical considerations. One of the most significant challenges facing DEWs is their power requirements. High-powered DEWs, particularly laser systems, require enormous amounts of energy to operate effectively. This presents several issues, especially for mobile platforms. For vehicle-mounted or man-portable systems, the energy demands of DEWs can strain existing power generation capabilities. Traditional power sources like batteries or generators may struggle to provide the necessary output, especially for sustained operation. This challenge is particularly acute for airborne platforms, where weight and space constraints are already significant factors. To address this, researchers are exploring various solutions, including more efficient power generation systems, advanced energy storage technologies, and improvements in the efficiency of the DEWs themselves. Some proposed solutions involve novel approaches like chemical lasers, which generate their beam energy through chemical reactions rather than electrical power. The power challenge extends beyond just the operation of the weapons themselves. DEWs, especially high-powered lasers, generate significant amounts of waste heat. Managing this thermal load is crucial for maintaining the weapon's effectiveness and preventing damage to the system itself. This necessitates the development of advanced cooling systems, which in turn require additional power and add to the overall system complexity. As we contemplate these energy challenges, we might reflect on broader questions about power and energy in our technological society. The immense energy requirements of DWs serve as a microcosm of our civilization's growing energy needs. How do we balance the desire for increasingly powerful technologies with the realities of energy production and its environmental impacts? The development of DWs, with their extreme power demands, pushes us to confront these questions in a very tangible way. Another significant challenge facing DWs, particularly laser-based systems, is the issue of atmospheric effects. As a laser beam travels through the atmosphere, it interacts with air molecules, dust particles, and water vapor. These interactions can cause several detrimental effects. 1. Scattering. Particles in the air can scatter the laser light, reducing the amount of energy that reaches the target. 2. Absorption. Certain wavelengths of light are absorbed by atmospheric gases, again reducing the energy delivered to the target. 3. Thermal blooming. The heat generated by the laser beam can cause the air it's passing through to heat up and expand. This creates a lens-like effect that can defocus the beam, reducing its effectiveness. 4. Turbulence. Atmospheric turbulence can cause the beam to fluctuate and spread out, degrading its focus and effectiveness. These atmospheric effects become more pronounced over longer distances and in adverse weather conditions like fog, rain, or dust storms. As a result, the effectiveness of laser-based DWs can be significantly reduced in certain environments or at extended ranges. Researchers are working on various solutions to mitigate these atmospheric effects. These include adaptive optic systems that can compensate for atmospheric distortions in real time, multi-wavelength lasers that are less affected by certain atmospheric conditions, and sophisticated tracking and targeting systems that can maintain a precise lock on the target despite atmospheric interference. As we ponder these atmospheric challenges, we're reminded of the complex and often unpredictable nature of our environment. The difficulties faced by DWs in penetrating the atmosphere serve as a humbling reminder of the power of natural forces. Even as we develop increasingly advanced technologies, we remain subject to the fundamental properties of the world around us. This interplay between human ingenuity and natural limitations is a recurring theme in the history of technology, prompting us to reflect on our place within the broader ecosystem of our planet. A third major challenge in the development and deployment of DWs is their cost. While DEWs may offer cost savings in terms of ammunition over time, their initial development and deployment costs can be substantial. The advanced technologies required for effective DWs, including high-power lasers, precision optics, sophisticated tracking systems, and specialized power and cooling systems, are often cutting-edge and expensive. This high cost can limit the widespread adoption of DWs, especially for smaller military forces or nations with more constrained defense budgets. Moreover, the cost challenge extends beyond just the weapons themselves. The integration of DWs into existing military platforms and doctrine requires significant investment in training, logistics, and support infrastructure. Military personnel need to be trained in the operation and maintenance of these complex systems, and new tactics and strategies must be developed to effectively utilize DEWs in combat scenarios. The high costs associated with DWs also raise questions about the economics of warfare and defense. As military technologies become increasingly sophisticated and expensive, how does this affect the balance of power between nations? Does the development of DWs contribute to an arms race that favors wealthier nations, potentially exacerbating global inequalities? These are complex geopolitical and economic questions that we must grapple with as DW technology advances. Despite these challenges, many nations and military organizations see the potential benefits of DWs as outweighing their drawbacks, leading to continued investment in their development. Let's now turn our attention to the current status of DWs and their potential applications. Several countries, including the United States, China, Russia, and Israel, are actively researching and developing DW technologies. While these weapons are not yet widely deployed in conventional warfare, they are beginning to see limited operational use, particularly in areas like counter-drone operations and short-range defense systems. The United States, in particular, has made significant strides in DW development. The U.S. Navy has deployed laser weapon systems on ships for testing and limited operational use. These systems have demonstrated the ability to disable small boats and drones, showcasing the potential of DWs in maritime defense scenarios. Similarly, the U.S. Air Force has been exploring the use of airborne laser systems for missile defense. While early attempts at large-scale airborne lasers face significant technical challenges, ongoing research is focused on more compact, tactically viable systems that could be mounted on fighter aircraft or other smaller platforms. In the realm of ground-based systems, several nations have developed and tested DEWs for applications like counter-rocket, artillery, and mortar, CRAM, defense. These systems aim to use high-powered lasers or microwave emitters to disable incoming projectiles, potentially providing a more cost-effective alternative to traditional kinetic interceptors. One of the most promising near-term applications for DWs is in counter-drone operations. The proliferation of small, commercially available drones has created new security challenges for both military and civilian entities. DWs, particularly laser-based systems, offer a potential solution for engaging these small, agile targets quickly and cost-effectively. As we consider these current and emerging applications of DWs, it's worth reflecting on how they might change the nature of conflict and defense. The ability to engage threats at the speed of light with potentially unlimited ammunition could dramatically alter tactical and strategic calculations. How might the widespread deployment of DWs affect deterrence strategies, crisis stability, and the overall balance of military power? Moreover, the development of DWs raises important questions about the future of warfare and the role of human decision-making in increasingly automated defense systems. As DWs become more sophisticated and potentially integrated with artificial intelligence for targeting and fire control, how do we ensure that human ethical judgment remains a central part of military operations? These questions lead us naturally into a discussion of the ethical considerations surrounding DWs. As with any new military technology, the development and potential use of DWs raise a host of moral and legal issues that deserve careful consideration. One of the primary ethical concerns regarding DWs is their potential for use in non-lethal or less lethal applications. While this might seem like a positive development at first glance, after all, wouldn't a weapon that can disable without killing be preferable? It raises complex ethical questions. For instance, the availability of non-lethal DWs might lower the threshold for the use of force in certain situations. If military or law enforcement personnel believe they can neutralize a threat without causing fatalities, they might be more inclined to use force in situations where negotiation or de-escalation might otherwise have been pursued. This could potentially lead to an increase in the overall frequency of forceful interventions, even if individual incidents are less likely to result in loss of life. Furthermore, the long-term effects of some DWs, particularly those using microwave radiation, are not yet fully understood. While these weapons are designed to be non-lethal, there are concerns about potential long-term health impacts from exposure to high-powered electromagnetic radiation. This uncertainty raises ethical questions about the use of weapons whose effects may not be fully known or understood. Another ethical consideration is the potential for DWs to be used for crowd control or other domestic security applications. While the ability to disperse crowds or disable threats without using lethal force might seem appealing from a law enforcement perspective, it also raises concerns about potential abuse. Could DWs be used to suppress legitimate protest or dissent? How do we balance the potential security benefits of these technologies with the need to protect civil liberties and human rights? These questions become even more complex when we consider the potential for DWs to be used covertly. Unlike traditional weapons, many DWs could potentially be used without leaving obvious physical evidence. This could make it difficult to hold actors accountable for their use, potentially enabling human rights abuses or other unethical applications of force. The development of DWs also raises important questions about arms control and international law. Currently, there are no international treaties specifically governing the development or use of DWs. As these weapons become more prevalent, there will likely be a need for new legal frameworks to regulate their use and prevent potential abuses. Some experts argue that existing international laws governing armed conflict, such as the Geneva Conventions, should be sufficient to regulate the use of DWs. Others contend that the unique characteristics of these weapons, their potential for non-lethal use, their speed of light effects, and their potential for covert application necessitate new, specific legal agreements. As we grapple with these ethical and legal considerations, it's crucial to remember that the development of military technology doesn't occur in a vacuum. The choices we make about how to develop and deploy DWs will have far-reaching implications for international relations, human rights, and the future of warfare itself. Moreover, the ethical implications of DWs extend beyond just their immediate military applications. The technologies underlying DWs have potential dual-use applications in civilian sectors. For example, high-powered lasers developed for military use could have applications in fields like materials processing or space exploration. Similarly, advances in power generation and cooling systems driven by DW research could have implications for clean energy technologies. This dual-use nature of DW technology raises questions about the relationship between military and civilian research and development. How do we balance the potential benefits of technological advancement with the risks associated with the proliferation of potentially dangerous technologies? How can we ensure that scientific progress driven by military needs also benefits civilian society? As we ponder these weighty ethical considerations, it's worth taking a moment to reflect on the broader philosophical implications of DWs. These weapons, with their ability to project destructive force at the speed of light, in some ways represent the culmination of humanity's long history of developing ever more powerful and precise tools of war. They prompt us to consider fundamental questions about the nature of conflict, the limits of technology, and our responsibilities as a species capable of wielding such formidable power. In many ways, the development of DWs serves as a mirror, reflecting our own capabilities, fears, and aspirations back at us. They challenge us to confront difficult questions about our values, our priorities, and the kind of future we wish to create. As we continue to push the boundaries of what's technologically possible, it becomes ever more crucial that we also push ourselves to engage with the ethical and philosophical implications of our creations. Now, let's turn our attention to an aspect of DEWs that often captures the public imagination: their role in conspiracy theories and popular culture. The futuristic nature of DEWs, combined with the secrecy often surrounding their development, has made them a fertile ground for speculation and conspiracy theories. One common conspiracy theory suggests that governments or other powerful entities are secretly using DEWs for nefarious purposes, such as mind control or weather manipulation. These theories often point to unexplained phenomena or health issues as evidence of covert DEW use. For example, some conspiracy theorists have attributed symptoms reported by diplomats in what's known as Havana syndrome to the use of secret-directed energy weapons. Another prevalent conspiracy theory involves the idea that DWs are being used to start wildfires or cause other natural disasters. Proponents of this theory often point to the intensity and seemingly unnatural spread of some wildfires as evidence of DW involvement. It's important to note that these conspiracy theories are not supported by credible scientific evidence. While DWs are indeed powerful technologies with significant military potential, their capabilities are often exaggerated or misunderstood in these conspiracy narratives. The persistence of these conspiracy theories raises interesting questions about the relationship between advanced technology, secrecy, and public trust. In an age where the gap between cutting-edge military technology and public understanding of science can be significant, how do we foster informed public discourse about these issues? How can governments and scientific institutions maintain necessary security while also promoting transparency and combating misinformation? Moreover, the prevalence of DW conspiracy theories serves as a reminder of the power of narrative and imagination in shaping public perception of technology. Even as scientists and engineers work on the technical challenges of DW development, these weapons have already taken on a life of their own in the public imagination, featured in everything from science fiction stories to online conspiracy forums. This cultural aspect of DWs is worth considering as we think about their broader implications. Technologies don't exist in isolation. They're embedded in cultural contexts that shape how they're perceived, developed, and used. The stories we tell about DWs, whether in fiction, in policy debates, or in conspiracy theories, can influence public opinion and potentially even policy decisions. As we navigate the complex landscape of DW development and deployment, it's crucial that we strive for a balanced, informed perspective. This means acknowledging the real capabilities and limitations of these technologies, engaging with the ethical and strategic questions they raise, and working to foster public understanding that's grounded in scientific reality rather than speculation or fear. Looking to the future, the trajectory of DW development remains uncertain. While significant technical challenges remain, ongoing research and development efforts continue to push the boundaries of what's possible. It's likely that we'll see increasing integration of DEW technologies into military systems in the coming years, particularly in areas like missile defense, counter-drone operations, and point defense for military vehicles and installations. However, the future of DWs isn't solely a matter of technological development. The path forward will be shaped by a complex interplay of factors including geopolitical considerations, ethical debates, legal frameworks, and public opinion. The choices we make today about how to develop, regulate, and potentially deploy these weapons will have far-reaching consequences for the future of warfare and international security. One potential future scenario involves the widespread adoption of DWs leading to a fundamental shift in military doctrine and strategy. In a world where speed-of-light weapons are commonplace, traditional concepts of deterrence and defense might need to be reevaluated. The ability to strike instantly across vast distances could compress decision-making timeframes, potentially increasing the risk of escalation in crisis situations. On the other hand, the precision and potentially non-lethal capabilities of DEWs could lead to a future where military operations are conducted with greater discrimination and reduced collateral damage. This could potentially align with evolving norms in warfare that emphasize the protection of civilians and minimization of unnecessary destruction. Another possibility is that the development of effective countermeasures against DEWs could limit their military utility, leading to a balance similar to that seen with other military technologies throughout history. For example, advances in materials science could potentially lead to new types of armor or shielding effective against laser or microwave weapons. As we consider these potential futures, it's worth reflecting on our role in shaping the path forward. The development of DEWs, like any powerful technology, presents us with both opportunities and challenges. How we choose to navigate these will say much about our values, our foresight, and our capacity for responsible stewardship of our technological capabilities. In conclusion, directed energy weapons represent a fascinating intersection of advanced physics, cutting-edge engineering, military strategy, and ethical philosophy. From the high-energy lasers that can disable drones and missiles, to the high-power microwave systems that can disrupt electronic equipment, to the still theoretical particle beam weapons that could one day be deployed in space, DEWs offer capabilities that were once the realm of science fiction. These weapons promise speed of light engagement, potentially unlimited magazines, and the ability to strike with unprecedented precision. Yet they also present significant challenges, from the immense power requirements and atmospheric effects that complicate their use, to the ethical and legal questions raised by their potential for non-lethal applications and covert use. As we've explored in this discussion, the implications of DEWs extend far beyond the battlefield. They touch on fundamental questions about the nature of conflict, the balance between security and civil liberties, the responsibilities that come with advanced technological capabilities, and even our understanding of the physical world around us. The development of DEWs serves as a microcosm of our broader relationship with technology. It highlights the dual-use nature of scientific advancement, the complex interplay between civilian and military research, and the challenges of managing powerful technologies in an interconnected world. Moreover, the cultural impact of DEWs, from their role in science fiction to their place in conspiracy theories, reminds us of the power of imagination and narrative in shaping our perception of technology. As we move forward, fostering informed, nuanced public discourse about these weapons will be crucial in ensuring that their development and potential use align with our shared values and aspirations as a global community. As we stand on the cusp of what could be a new era in military technology, we're called upon to exercise not just our scientific and engineering prowess, but also our ethical judgment, our foresight, and our wisdom. The choices we make about DEWs today will help shape the world of tomorrow. In the grand tapestry of human progress, DEWs represent just one thread, albeit a significant one. They remind us of our remarkable capacity for innovation, our ability to unlock the fundamental forces of nature and bend them to our will. But they also serve as a potent reminder of the responsibilities that come with such power. As we continue to push the boundaries of what's possible with directed energy, let us do so with a keen awareness of the broader implications of our actions. Let us strive to ensure that these powerful tools are developed and, if necessary, used in ways that contribute to a more secure, just, and peaceful world. In the end, the story of directed energy weapons is our story, a tale of human ingenuity, ambition, and the ongoing quest to understand and shape the world around us. As we write the next chapters of this story, let us do so with care, wisdom, and a deep commitment to the betterment of our shared human condition. Thank you for joining me on this exploration of directed energy weapons. As we've seen, this is a topic that touches on a wide range of disciplines and raises profound questions about technology, ethics, and the future of human conflict. I encourage you to continue exploring these issues, to engage in thoughtful dialogue about the implications of these technologies, and to approach the topic with a balance of curiosity and critical thinking. Remember, in our rapidly evolving technological landscape, staying informed and engaged is crucial. Whether you're a scientist, a policymaker, a member of the military, or simply a concerned citizen, Your voice and your perspective matter in shaping the future of these technologies. As we close this discussion, I invite you to take a moment to reflect on what you've learned. Consider the potential benefits and risks of DEWs, think about the ethical questions they raise, and ponder how you might contribute to informed, responsible decision-making about these technologies in your own sphere of influence. Thank you for your attention and engagement. Until next time, stay curious, stay informed, and keep exploring the fascinating intersections of science, technology, and human values.